Ну, кто собирается, пусть придет.
Okay, so I think we can start this special session, this conference, which is a memorial session of Mitya Dьяконов. And let me just say a very few words to start and to warm up. So for many of us, like here, Mitya was a good friend, and for many of us, he was a teacher, and for many, he was a colleague. I was very fortunate to know him in all these roles, and sort of he played a very important role for actually in, also in scientific careers of many of us. Just 1 minute, just one small episode. So I was I don't know, was it already 30 years ago or something like this. I was in Media, and he gave me a preprint that reprint of a paper that he just received, and he told me, look at it, seems to be interesting, maybe you want to study it. And that's it. And then I read it and found that it's very interesting. So the paper was actually a paper by Jacques, who sits here, and it was about localization on a Kale tree, and this played kind of a major role in sort of my scientific life. That's what actually was first triggered me to study localization, to study supersymmetry, and after scientific career of or life of Jan, and actually of a few other people around. Yeah, that's and this is just one small episode. And
Wyatt.
I could talk about Mitya for hours, but that's of course not what I will do. And so we will. And there are many people here who could do this, but we decided that three of us will give some presentations about Mitya's scientific sort of work, and also about him as a human being, about our friend and colleague. And so, and Mitya will start, please.
Yeah, thank you. I was working with Mitya approximately 30 years together, and I am co-author of approximately half of his works. So for this reason, it's natural to talk about his scientific achievements, and I'm going to do this. So my talk is called Scientific Life of Dmitry Dьяконов. So Mitya entered our theory division of Petersburg Nuclear Physics Institute in 1972. He became a PhD student of Professor Anselm. And Professor Anselm was one of very few that days who still believes in quantum field theory. Because this was days when quantum field theory was considered as not a self-consistent object, because due to famous nullification of the charge. And our department, which were working under Vladimir Gribov, was a field center of Regis theory, of course. But Mitya and his supervisors keep the interest of the field theory. He was believing in the field theory from his very youth to the end of his days. His first paper, which appears in 1975, deals with spontaneous breaking of chiral symmetry in 1+1 dimensional asymptotically free model of Gross-Navier. In fact, a little bit more general models than Gross-Navier. Surprisingly, it's an asymptotically free theory, which was discovered that it is asymptotically free as early as 1959, so well before real discovery of asymptotically free theory. But Mitya came later, and he was dealing with breaking of chiral symmetry in this theory in perturbation theory. So he calculated this in chiral condensate in 1+1 dimension. But already at that time, he realized that this approach cannot be justified in quantum chromodynamics. His next two papers deal with electroweak theory, because his supervisor was a great expert just in electroweak theory. So Mitya calculated, by the way, it's not very simple calculation. He calculated corrections to Coleman-Weinberg potential, radiative corrections, and also radiative correction to the Weinberg angle. So that days, for the very young person, it was really a very complicated calculation, and he started his career with these calculations. This is Mitya that days. It's a photo of 1977. So that days was revolutionary days, if you know. In 1973-74, C quark was discovered, and quantum chromodynamics arrives, and asymptotic freedom arrives, and this all influenced Mitya a lot. He was deeply impressed by this revolution. And he became very enthusiastic about the physics of hard processes in QCD. And he begins, in 1975, together with Mark Strickman, he translates to Russian a very famous book of R. Feynman, Interaction of Photons with Hadrons. And of course, when he was translating, he was carefully reading this book, and he was deeply impressed by this book. And so he immediately switched to the physics of hard processes in quantum chromodynamics. Of course, it was very fashionable topic that days. And in fact, his very first paper was the production of particles with large transverse momenta. So to read that, the physics, the production, so it's a hard process at high energies. It was published in Soviet Journal of Nuclear Physics in 1973. It's indeed his first paper. And it was done on the second year of his PhD scholarship. Next paper was on the same topic, because he was already with his scientific supervisor, Alexei Ansel. At that very time, hard physics already becomes one of the main points of investigation in our department. We switched from Regge theory to this topic. And it happens mainly due to the famous Gribov-Lipatov papers. Mitya was very interested. Is it possible to reconcile Parton model, which was Feynman-Bjorken Parton model, with quantum field theory? It was a very non-trivial question that days. Any quantum field theory, for example, quantum chromodynamics. We know now that the answer is yes, due to asymptotic freedom. For this reason, to investigate the question, Mitya joined Yuri Dakshitzer and Sergei Troyan, who was already occupied with this problem. For a few years, they investigated approximately all known hard processes, and for example, the simplest one, which is Drell-Yan, the production of mu plus mu minus pair. It's a classical hard process. And they published a number of papers which immediately became well known. They became famous with these papers. And they derived, in these papers, the famous DDT formula. DDT stands for Dьяконов, Dakshitzer, Troyan. And now it's even in handbooks, it's written DDT formula. So this formula expressed the cross-section for Drell-Yan process in terms of Parton distributions in hadrons, which in principle can be measurable in deep inelastic, and Sudakov, so-called Sudakov double logarithmic form factor, which looks like that. In fact, it was one of the first quantitative formula in QCD which allows to predict not only a number, and not only something qualitatively, but a whole function of transverse momentum, which follow directly from the first principles of QCD. These papers are still very well known. For example, their review about DDT formula. One of these papers has at least 800 citations, and what is funny, that last citations are from 2019, so they are still cited. Unfortunately, in principle, it looks like that all his life, all his scientific career, Mitya should devote to the physics of hard processes, to perturbation theory in quantum chromodynamics, but it was not the case. In fact, he was not satisfied by perturbative treatment of QCD. He feels that the essence of quantum chromodynamics is in fact non-perturbative. He used to say that all physics of hard processes is contained in fact in Leonard-Wiechert potential. Of course, it's a joke, but a part of deep truth, there is a part of deep truth in this statement. So he always thought that this physics of hard processes cannot answer deep and interesting questions in quantum chromodynamics. For this reason, he looks for the opportunity to switch to something non-perturbative in quantum chromodynamics. And that days, it was a time when QCD sum rules, so it stands for operator expansion, appeared. And Mitya, together with more younger people, Jung and Baletsky, they use these sum rules in the new area. They predict an exotical particle, which is called hermaphrodite, which consists of quark, antiquark, and gluon, so 3 particles. And they predict them with the help of QCD sum rules. It was one of the first predictions of the QCD sum rules, because all what was before that was not predictions, in fact, but they were postdictions. They explained something which was already known that days. It was a very complicated and interesting paper, but he was still not satisfied by some rules as well. Some rules it's an expansion at large Q squared by some condensates. And they consider these condensates, so chiral condensate, gluon condensate, and so on and so forth, as given quantities. But he used to repeat that the problem is not to use these quantities, but the problem is how to calculate them from QCD. So for this reason, he organizes and leaded the group of people who started to learn and discuss non-perturbative aspects of QCD. And this is the way by how I became his co-author, because I was in this group, and we all together tried to understand what can be non-perturbative in quantum chromodynamics. One of the first problems he deals with was the so-called U1 problem. So you know very well that one of the main phenomena which happens in quantum chromodynamics is spontaneous breakdown of chiral symmetry. The other is confinement, of course, but maybe a spontaneous breakdown of chiral symmetry determines more properties of hadrons than even confinement. So from this point of view, spontaneous breakdown of chiral symmetry, we should have some Goldstone particles, according to Goldstone's theorem. So there should be 9 massless particles. However, in nature, we have only 8 massless particles. And the 9th particle, which is eta prime, is massive. Why it is massive? This problem is called U1 problem. It has direct relation to the Adler anomaly, because the U1 current, U1 chiral current, it is actually broken by this Adler anomaly. Non-conservation is in fact related to the topological charge of the field, which is defined as the following quantity, that where F is a strength tensor for Young-Mills field. We know that the potential energy in Young-Mills theory is a periodic function, if in some number which is Chern-Simons number. or not all of them is present, but not all of it is present, but there are still something else. And it's a periodic function in this quantity k. And topological charge is just a change of k in the process where you go from one minima of potential to another minimum potential. Actually, U1 problem that days was solved by two people, Witten and Veneziana, and they calculated the mass of eta prime meson, which appeared to be related with condensate of topological charge. So it has direct relations to the penetrability of these barriers which are in the potential energy, which are related with transitions from one minima to another minima. So Mitya also contributed to this problem. They published a number of papers, partially with Misha Edis, or maybe all of them were with Misha Edis, but and understand this problem, and then they understood this problem completely. And this also gave a strong impression on Mitya, because non-zero mass of eta prime meson is a direct proof, experimental proof, of the fact that QCD barriers are penetrable in quantum chromodynamics, that these transitions from one minima, from one vacuum minima to another, rarely take place. Instead, there is a famous theta problem appears. The theta problem is that if you have such a situation that barriers are penetrable, then of course there can be some states which corresponds to the non-zero quasi-momentum. So the whole vacuum can move along this direction with some quasi-momentum. It's like in solid-state physics, of course. This is called theta problem. And the problem is that such states, which are not forbidden, of course, they break down conservation of CP, and so it means that it should appear not only in electroweak interaction, but in the strong interactions as well. So U1 problem indeed deeply impressed Mitya. He started to believe that instantons can play a very important role in QCD vacuum. And for this reason, we started a program to construct vacuum of QCD solely out of instantons and anti-instantons. This was a large program, and it continued almost for 15 years. And we achieved our goal at the very end. So for the first we need some method for accounting arbitrary configurations in the functional integral, not just quasi-classical configurations, but arbitrary ones. And this method is a Feynman variational principle. You can indeed try the configuration, any configuration, and then you are guaranteed that the result that you obtained can only increase the vacuum energy, not decrease it. So it's some approximation like Reed's variational principle in quantum mechanics. So we tried this method in quantum mechanics. We invented approximate method of how to calculate quantum determinants, and then we returned back to QCD. We choose as a trial ansatz. Then if you have some variational principle, you can try some variational ansatz and trial ansatz, and then you minimize its parameters, and it can be a good approximation to the real thing. We choose this trial ansatz to be instanton liquid, and statistical sum of QCD in the instanton liquid becomes a statistical sum, just a classical statistical sum for particles of different size, orientation and color space, and with a coupling constant which plays a role of temperature, but this temperature depends on the average size of your particles in your liquid. We solve this problem and obtain. So the coupling constant freezes, and so infrared problem is solved in this vacuum, and the size is much smaller of the instanton in this instanton liquid is much smaller than the distance between them. So it demonstrates for us that approximation of instanton liquid is indeed self-consistent. So this is a ratio of distance to the average size of the instanton. It's 3.1, and this is the freezed number for the coupling constant. We calculated in two-loop approximations all quantities in Young-Mills theory. in the instant-on-liquid model. So gluon condensate, for example, and correlator of topological charges, and all of them were calculated as some constants in front of the infrared cutoff in quantum chromodynamics. So then we calculate distribution of instantons and sizes and so on and so forth, in approximately all possible quantities. It appears that the results are satisfactory, in spite of the fact that our trial answers was rather crude. And they all are very close to the phenomenology of the Young-Mills theory, if we accept that lambda Pauli Willis is something like 250 MeV. That days, the value of lambda was something less than 100. So I remember that all were laughing on us, because, of course, it's very far from the reality. But during years, lambda increases more than 2 times from experimental point of view, and now it's very close to our estimate. So it appears that during next 15 years. Here you see the distribution of sizes in the distribution in instanton sizes. This is the curve is our calculation, and the points are extracted from the lattice simulation. So you see this is also not very far from reality. So as we were satisfied by the instant-on-liquid in Young-Mills theory, then the next natural step was introduce light quarks in the instant-on-liquid. It was done in 1986. Introducing quarks into instantons, we want to explain how spontaneous breakdown of chiral invariance happened. What is the mechanism for it? And after some careful thinking, we realized that the mechanism is the delocalization of zero modes in the disordered instant-on-liquid. In fact, it's very close and very well familiar, at least for solid-state theorists. In spirit, it is close to the well-known P.V. Anderson model, but the difference is that it happens at any density of instantons, even at a very small one. The reason is known. It's called Anderson's theorem, as I understand. The reason is that the overlap integral between zero modes behaves as a power of the distance between them, and this is just a power which provides for you that it exists at every, even very small density. And what we discussed this morning is just I don't understand how it can disappear. It is one of the problems. We obtained a chiral condensate, and which appears to be 255, and experimentally it is 250. Of course, it's a coincidence, because it's much better than our accuracy. And we derived effective quark theory, which appears after integration over all instantons. We bosonize it and derive expressions for all quark correlators in the instant-on-liquid. Of course, according to the spontaneous breaking of symmetry, we obtained massless pions and traced the solution of U1 problem. We calculated the mass of eta prime meson. We calculated the axial coupling constant for pi meson, which appears to be 98, experimentally 92. We calculated correlators in all channels in Euclidean region of momentum, and this curve was obtained approximately 10 years later. You see our curve versus experimental points. So you also see that some agreement takes place. Due to breakdown of chiral symmetry, quark acquires a mass, some effective mass. This effective mass depends on the virtuality of the quark, and it was measured also on the lattice maybe 10 years after, and you see how it corresponds to our calculations. At zero virtuality, it appears to be 350, And it is also good for phenomenology. So in a sense, we derived constituent quark model, and which was a problem for many, many years. And we see that there are indeed two sizes in the vacuum of quantum chromodynamics, and size of constituent quark, which is 1 over size of the instanton, is rather small. Next step was, it happens in 1987, we integrate out all quarks, and after that we can derive effective chiral Lagrangian, which is the effective Lagrangian describing properties of QCD at small energy, small momenta. Of course, it depends on the pion. Of course, on the pion field, which is Goldstone particles, and it appears that it depends on our effective mass. And it is valid in the large range of energy, which is approximately 600 MeV, 1 over size of the instanton. It sums up all powers of pion field and all its derivatives. Next step was, of course, to try the chiral quark soliton. Because if you know, in 1985, Witten proved that at large number of colors, all baryons should be solitons of chiral Lagrangian. So it was, the natural idea was to try our Lagrangian to construct baryons. We were very interested in the paper of Witten, but we failed to understand it, to be honest, and so for this reason we derived all the results ourselves. Then we tried to obtain nucleon properties in the Skir model, which was most popular that days. But three authors, Witten, Atkins, and Napi, was faster than we, and they published it before us. For this reason, we turned our paper into a review lecture and published it in 1986 and called it baryon as soliton. So next idea was quite natural. Skir model is a very crude approximation, just an artificial model. And we had a thing which we think is just a good chiral Lagrangian. So just to try our Lagrangian and construct a baryon. We did it, and we discovered that nucleon in this Lagrangian appeared as a bound state in some self-consistent pion fields. And fluctuations of pion field are suppressed by the number of colors. Next year, it was 10 years at least, next years we were working on this model, which proved to be rather successful and give all known properties of baryons with accuracy 10 or 15%. So these are some properties of nucleons, some basic properties, sigma term, axial constant, and so on and so forth. And they indeed are rather close to experimental data. And we did not only basic properties, but also some high energy properties. For example, you see here the anti-quark structure function. And this is some experimental data on it. This is high energy characteristics of the nuclei. And I choose this to display because this function principally cannot be calculated in any other model. Neither in quark model nor in the Skir model, because they are not self-consistent. The great advantage of our theory of nucleons is that it is a self-consistent relativistic theory. For this reason, it should answer any question. Maybe incorrectly, but at least you can ask this question. So we did it for some time, and we investigated this problem, this model to the very end, and we understood that model is in fact interplay of quark model and Skir model, but should substitute both of them because it's simply better. And we described also not only nucleons and some ground states, but we described all baryon resonances. There are a lot of baryon resonances. We describe all baryon resonances under 2GeV and see that there are no extra or no missing states. For example, in the quark model, you have hundreds of missing states. But the problem was that the model contains also exotic states, so not states which consist of 3 quarks, but consist of 5 quarks. And in fact, and the first of these states is anti-decoupled. And we understood after a while that these exotic states are unavoidable, not only in our model, but in any model which is based on the limit and colors goes to infinity. They are absent in the quark model only for such a trivial reason that this model fails to account for massless pions. Quark model doesn't account for pions, but at that very moment you account for pions, you are left with exotic states. So we tried to do this seriously, and in 1997 we made a very specific prediction of pentaquarks, this anti-decoupled with the lightest state, theta plus, which has a mass 1540 and rather small width, only few MeV. This prediction was a boom, made a big boom among experimentalists. So all groups all over the world immediately tried to measure it. And at the first stage there were 25 at least by different groups, 25 successful measurements, so to say discoveries of pentaquarks, but then they followed at least 20 unsuccessful measurements. So still up to now I have to say that the status of our anti-decoupled is indefinite. In fact, now pentaquarks are discovered, pentaquarks with heavy quarks. These are not our pentaquarks, but we still hope that at one day the pentaquark can be discovered. So you see that during 15 or 20 years we were doing instantons, and we go through the whole theory of strong interactions from Young-Mills theory to nuclear physics, and we saw no failures, no real failures, maybe except pentaquarks. And we saw that instanton vacuum is phenomenologically quite successful, but it has no confinement. There are no confinement in the instanton vacuum. Of course, we were disappointed by this fact and tried to understand how confinement can happen. But to be honest, even criteria of confinement is rather complicated. Normally, it's related either with Polyakhov's line, which is an order parameter for confinement, or with Wilson loop, which should behave as an exponential of minus surface. But all these objects are ordered non-abelian exponents, and it is not easy just to work with such an object. For this reason, we tried to simplify this, and we understood after a while that it is possible to write down a formula for the Wilson loop or for Polyakov's loop, a representation for it, which made it abelian, but at the price of additional functional integral. It's our formula for the Wilson loop, and it appears that there is a very beautiful formula. We derived it, which is integral. For example, in the simplest case of SU2 group, it looks like that. You integral over some vector, unit vector in the space, and this along the contour, and with an action which is with the Zumina term, and which has an additional term. This will produce for you non-abelian ordered p exponent. In fact, this formula appears to be rather general. It works for any group and in any theory. And also, it's valid for gravity. For example, parallel transporter, which is the integral of Christoffel symbol, can be presented exactly in this way. And also, you can, using this formula, you can not only derive a formula for a Wilson loop, but you can derive so-called non-abelian Stokes theorem. So you can present it as an integral over some surface. And in fact, so it greatly simplified calculations when you need to calculate the average of this Wilson loop or something else. Another attempt to do something with confinement was to try to to rewrite Young-Mills theory in some dual variables, because everyone in literature advise you just to consider Young-Mills in the dual variables. It should be simpler. So we tried to make it seriously, and we start with the lattice QCD, which is a theory with SUN matrices put on the links and the Wilson action. What are dual variables? Dual variables are angular momenta of Wigner SUN D functions. They are gauge invariant, by the way. So we not only have dual theory, but we also have a theory in gauge invariant terms. We derived action for dual variables in Young-Mills theory on the lattice, and it appears to be associated with SUN Raka symbols. Just what about Reshetikhin was talking. Integration in U matrix is substituted by summation in angular momentum with a simple Gaussian weight corresponding to Young-Mills action. But we're also interested in the continuum limit of this lattice theory. And in dual variables, it corresponds to the Panzana-Redge semi-classical approximation for Raka symbols, which is very well known, leads in turn to the Redge, so-called Redge gravity. The continuum limit of all this is Einstein action for D equal to 3 and SU2 group. Young-Mills action, which is a simple quadratic term here, plays a role of SR, which softly breaks invariance under coordinate transformation. And this Einstein gravity, of course, has a coordinate transformation symmetry. But without Young-Mills action, we are left with topological theory. So if we just cancel Young-Mills term, then it's just topological theory. In fact, this result was proved previously by Witt. And he proved that gravity in D equal to 3, this is what I was talking about, is a topological theory. So there is no gravity in D equal to 3. But and it was before us, of course. But we were able to construct the infinite set of topological theories with arbitrary group and space-time dimensions. They all have dual symmetry, which has it is far more powerful than symmetry under coordinate transformation. It has much more parameters. And all the theories are topological. Unfortunately, explicit construction of this theory, we have a principle, but explicit construction was done by us only for D equal to 4 in case of SU2 group. It is an interesting problem, but we failed to solve it in some beautiful way. But nevertheless, all this infinite set of topological theories are still there. Adding to this topological theory, simple SR term, we obtain Young-Mills theory in dual gauge invariant variables. It's an interesting rewriting of Young-Mills theory. Maybe it's productive. We tried many things with it, but nothing very interesting came out. So we continue our investigations about confinement, discussing with many people. This is a discussion of Mitya with Hooft, and we're asking him what to do in a sense. But at the very end, the real step forward was done by von Baal and other people, which understood that instantons at non-zero temperature can be melted into new configurations, which are exact solutions of equations of motion in presence of non-trivial Polyakhov's line. At large distances, these configurations are self-doing diodes, but at large distances. So then we understood what to do, that we can do a vacuum out of these configurations, as we always do. And we started to calculate the quantum weight. It was our first result in the field. We calculated the quantum weights, say determinant of these configurations, together with our students, Nikolai Gromov and Sergei Slizovsky, and then used them as a building blocks to construct a vacuum model for confinement, which also contains confinement. So Dyn model of vacuum indeed can be constructed and even married with instanton liquids. So we can obtain some model which contains all phenomenological advantages of instant-on liquid plus confinement. It indeed contains confinement, phase transition, confinement, deconfinement, strings, Hagetort behavior of the spectrum, all what we need. Funny enough, it's even quite successful phenomenological. You see here the temperature of phase transition and topological condensate, and it's rather close to lattice simulations. 2, 3, 4, and infinity is the number of colors. Idea of phase transition behind it is a competition of non-perturbative and perturbative potential for Polyakhov's line. The picture is as follows. There is a perturbative potential calculated by Gross, Pisarsky, and Jaffa. Here it is, it's in red. And there is a non-perturbative potential from Dynes, which is here. And the real potential is the sum of two. And at some temperatures, the minimum is at the point pi equal to 1. So Polyakov's line is 1. And it's well known, it's an order parameter. And then it's well known that it is deconfinement phase. But when temperature diminishes, then a minimum comes to pi equal to 0. So this potential is larger. And it's confinement phase. All okay, we married everything, phenomenologically successful. But the main point is not here, because unfortunately it's an abelian confinement. It is exactly the confinement of type which was invented by Mandelstam, Polyakov, Hooft, and so on and so forth. But we think, in general, that it doesn't correspond to the nature, and the nature, the real confinement should be non-abelian. But it's a questionable question. It can be questioned. So, but what we can, we did. So another topic which Mitya did was a so-called Holy Grail function. It's my beloved problem in quantum field theory, one of the most interested, I would say. So maybe you know that in the standard model, due to instant-on transitions, baryon charge is not conserved. Cross-section of production with baryon number relation, with a number of particles which is large, which is inversely proportional to the coupling constant, is in fact exponentially small, but is a function of energy in the units of mass of sphalerol. Holy Grail function, which is standing here in the exponent, it has an expansion in this dimensionless energy. And the first term is just a gamma factor, which is instant-on action. The second term was calculated by Zakharov and Ringgold. Third term, which is epsilon squared, was calculated by us. And the fourth term was calculated by Dьяконов and Polyakov. So we calculate it's an expansion at small epsilon. But the question is, can it be that the cross-section becomes order of unity? There is no exponential suppression. And we investigated this question, and it appeared to be very deep, because it claims for a new general semi-classical approach. And we found this approach by a method, Landau method, in fact, method of singular complex trajectories. So trajectories which contribute to the functional integral determining this cross-section are first complex, second singular. And then, in principle, it is possible to find the Holy Grail function completely. And using this method and some ideas of Vladimir Gribov, we understood that this function, we prove a theorem, that this function is larger than 1/2, so cross-section cannot be very large. We formulate also, we understood and realized that there should be some non-perturbative kind of unitarity in semi-classical problems. So this means that you can calculate the contribution of instant-on and anti-instant-on by unitarity. You calculate the amplitudes with non-conservation of baryon charge and use dispersion relations to restore the contribution of instant-on aliens. For this reason, this is a way how to define correctly contribution of instanton and anti-instanton and derive correctly, not variationally as we did before, but correctly, mathematically correctly, instanton anti-instanton interaction as a Fourier transform of Holy Grail function. So simply, this interaction of instanton and anti-instanton is a Fourier transform of Holy Grail. And of course, we calculated few terms and tried to understand how far was our variational answers from the reality, from the mathematical reality. No, it appears not very far. Not exactly the same, but not very far. Last years of his life, Mitya was very much interested in gravity. First, he did it with me and his student Alexei Vladimirov. Mitya considers constrained gravity as just a low energy limit of some theory, like exactly in the same manner like chiral Lagrangian in the QCD. So constrained gravity is the lowest possible term, but in principle he was interested also in the next possible terms of this effective Lagrangian. Surprisingly, this problem was never done by anybody. And he published a paper together with Alexei Vladimirov, which performed a complete classification of the next possible terms, including torsion and interaction with half-integer integer spin particles. And then they constructed a systematic expansion in gradients, so to say, in the same manner as in effective Lagrangian. But then he realized that gravity contains the following, it was known, that gravity contains the following fundamental problem, which has nothing to do with that it is non-renormalizable theory. It's much deeper. The problem is trivial. If you consider the Einstein action, then you will see that this action is not positively defined. And both scalar curvature as well as determinant can be negative. This means that gravity theory, if the functional integral for gravity theory with any terms is always divergent. There are no stable states, there's no stable vacuum for gravity theory. And there is no way out. And that doesn't depend of is the gravity described by Einstein action or any other action. It can be always negative. Mitya thought about it, and he saw only one way out, how to define correctly gravity theory, quantum gravity theory. This way out is to consider metrics, tetrade to be precise, as being compound particle made of spinors. It was not his idea exactly. It was Vetterich who suggested this. So imagine that your tetrade is made out of spinors. Then still action can be negative. But because of the fermion nature of the tetrade, the underlying fermion nature of tetrade, all functional integrals with tetrade written in fermions cannot be divergent. They are still restricted by Pauli principle. So this is a way how to solve this fundamental problem. So he called this spinar gravity, and he started a long-standing program to investigate the spinar gravity. He published 1 or 2 papers, but as we know now, he had no time to complete it. And these are his last papers. And I remember, we worked together on Thursday, and on Saturday, he got very heavy heart attack and dies 3 days after. So this is the end of the story. Thank you. That's all.
Тяжело выступать после Вити. Он представил it's hard to talk after Vita. He presented a comprehensive description of Mitya's scientific life, and I will not even attempt to compete with him. And anyway, I didn't prepare any transparencies, so I'll just present some personal recollections of my work with Mitya, how it started, how it developed, what we did, and with emphasis on human part of this story. So it starts with the student years. In student years, I was one course, I believe, older than Mitya, so it was a gap between us, a small gap, and I don't think that we, of course, we met at the physics department of Leningrad State University, but we probably didn't know each other pretty well. But what happened, I graduated from Physical Mathematical School 239, and Mitya from another school 157, and it turned out that Mitya at the department became close friends with other graduates of 239, and so my friends were his friends, but we didn't interact too much during our student years. And then we both were at the Gribov seminar at the Petersburg Nuclear Physics Institute, and we started to work together after we both did some things. After I worked on string theory and what was at that time string theory, and tried to construct string field theory. I succeeded with light cone representation, which became my PhD. And Mitya worked, as Viti described, and his most famous work at this moment was this paper, DDT paper, which he did with Dakshitzer and Troyan. And then it turned out at some moment, I believe it was beginning of 80s, where we both were looking for next problem, and both were ready to switch to something completely different. And I need to tell you that at the Gribov department at that moment, nobody was very interested in field theory. Field theory, traditionally, department was about regions, region diagram technique, Gribov's region diagram technique, asymptotics, and so on. And field theory somehow was considered not quite the thing, as matrix was the real thing. And I remember that even Gribov for a long time was skeptical about quarks. At that moment, he probably already changed his mind. But so we, together, Mitya and me, we decided that we need to learn field theory, and especially low energy field theories and such methods as algebra of currents, anomalies, and all that stuff. And as Vita mentioned, we started to discuss, there was a very famous U1 problem, why we don't have the ninth light pseudoscalar meson. So we started to discussions, and scientific life at the department at that moment was organized in such a way that we had weekly seminars at Physical Technical Institute in the morning. And so Gribov seminar went forever, but at some starting in the morning, some about 2 or 3 o'clock it ended. So we usually came to the eatery at the scientist house in Lesnoy, and scientist house for non-Russian participants, it's such center of social life of scientists where there were different lectures, discussions, kids learned English, music, and so on. And there was a nice eatery where we usually came after the seminar to talk. And we talked mainly about physics, but okay, Pretty soon we switched to politics, and there were no political disagreements about participants. Everybody was skeptical about existing situation, and the only question was how it will end. And it was absolutely unclear. We spoke very freely because it was a closed circle, everybody knew each other, and we didn't care about anything else. But okay, you cannot talk about politics too much, so we switched back to physics. And the little I knew that in this very eatery will come after Mitya's funeral. Okay, anyway, after these discussions, we returned to Physical Technical Institute and discussed physics for remainder of the day, finishing late in the evening. And this was our rule for, I believe, a few months. And after that, we decided that we are ready to do something. And we started a new schedule of almost, of everyday work. And how it worked, I was at that moment employed at Metrology Institute, so in the morning I had to go there, and I showed up in huge Dьяконов's apartment on Suvorovsky Avenue about 3 o'clock, and from 3 to 2 at night we were doing physics. Our problem was U1 problem. We tried to understand, interpret Witten-Veneziana solution, how eta prime became heavy. Witte described it. We realized that it means that non-zero topological susceptibility means that in the correlator of two topological currents there should be a massless ghost pole, and this massless ghost pole means that barriers between energy vacuums in QCD are penetrable. So we understood this when we wrote complete set of normal and anomalous identities, current identities, and solved it with and found all residues and decay constant of pseudoscalar nonnet. Okay, before I proceed with this, I need to return to this Mitya's family and this huge Dьяконов's apartment. It was an old Petersburg cultural family, and it was a long corridor in that room, and the inhabitants were essentially Mitya's parents. His father, Igor Mikhailovich, was a famous scholar of ancient Middle East, and his mother was also she was an expert on English literature. She was also a professor at the university and Gerson Institute, and sister of Mitya's mother was a physicist. She worked at a Physical Technical Institute. So there was a rule that at 5 o'clock, there was a 5 o'clock tea in this apartment. So this 5 o'clock tea, there was a huge table. And everybody came to this table, and with these 3 professors, there were 5 or 4 graduate students always present, and some guests. And it was an enterprise for hour and a half. The soloist was Igor Mikhailovich, who was a great speaker and very extremely interesting speaker, and all kinds of things were discussed during this table, and probably these discussions were not less interesting than our scientific work. So every day at 5 o'clock we interrupted, and maybe 6:30 there was nice conversation with this tea table. So returning to physics, Mitya and me, so we worked out our work, and we started to write a paper. And paper, of course, we decided to write in English, and we didn't have problem with English. At least we were pretty, or both of us were pretty sure that we are absolutely fluent in English, so there was some fight who will write it. Somehow it was resolved, but the problem came with the articles. Every Russian speaker knows that incomprehensive thing in English is articles. So we agreed on the text, but the problem was with the Vic rotation. Is it the Vic rotation or simply Vic rotation? I don't remember who defended odd position, but we had two experts. So we first went to Igor Mikhailovich and asked him how it should be said. He told us something. I honestly don't remember what he told us. But then we went to Nina Yakovlevna. And Nina Yakovlevna, and we asked them separately. So no one of them knew what were our answers. And Professor of English Literature said the same. So I don't remember who surrendered, Mitya or me, but we accepted what his parents told us. And the problem was resolved. So this... What? I don't remember. I don't remember at this moment. If I will need to write it again, and I probably wrote it a number of times in my papers, but I don't remember. You should be born with these articles. Okay, so we worked, so we wrote our U1 problem paper. Then we also solved another problem. We wanted to obtain chiral Lagrangian, to derive chiral Lagrangian for quarks for low-lying mesons from QCD, and it was later elaborated by Vitya and Mitya. But at that moment, we also derived chiral Lagrangian, which was more crude, but we were very happy because we integrated anomaly, and we automatically obtained Wess-Zumina-Witten term with the proper coefficient, which just came from a calculation and not from an assumption. So this we wrote, and then our scientific ways parted, because as you just have heard, Mitya admired instantons, and I was much more skeptical about instantons. I didn't believe that they are the answer. So our further scientific routes went in different directions, but we preserved our friendship for the remainder of our lives. And there was a rule, both with Mitya and me: we never collaborated with people whom we didn't like personally. So I hope I can say it for Mitya that we liked each other. And we remained friends for a long time after that. And there was many things in our lives which intersected also. I remember many New Years. We celebrated New Year at the winter house of Mitya's parents. It is in Ushkova. So a large company came there and spent 2 days New Year, and we met New Year there with all games, charades, skiing, and many, many other interesting things. What else I can remember? There was time when the country opened, so we were very optimistic in the end of 80s, and I remember pretty well what impression was. Mitya was the first of us to go to US for a while. And he came back, and I remember we were sitting this time in my apartment, and he was describing his experience there. And I remember what made most impression on me. he told me that he told us, the company, that he rented a car and went from one university city to another. I don't remember, maybe from Ithaca to Ann Arbor. And he missed proper exit. So he explained me that he needed to return about 50 miles to another exit, and all that stuff looked completely fantastic to me at that moment. Okay, so there were a lot of good time there, and we were very optimistic, and unfortunately it did not came that way, and of course Mitya left us prematurely, but I'll always remember him with very good feelings. Thank you.
Okay, and so now I want to welcome Misha Semyonov-Tsenchansky to give kind of a last presentation of the session.
Well, it's a difficult task for me because I must tell. Sorry. I just wanted to look sometimes at my notes. So it's a difficult task to me because, well, it's a summary of almost an entire life, which we spent together since the age of 18. We were not acquainted at school because our schools were different. But when I was probably in my second year in the university, or maybe it was the first year in the second semester, Mitya came up to me in the corridor of physical department and said that he knows about me and he would like to be friends with me. As a matter of fact, each of us belongs to a family with a long history, and we were aware of each other's existence much earlier than we got acquainted. But it so happened that we never met personally. My mother was a student of Nina Dьяконова back in 1930s, and then we just had some rumors about each other ever since. And so then we became friends, and we got this friendship grew stronger and closer ever since, and that for 45 years, I guess. I should say that, well, what's rather unusual with Mitya was his very early, very serious dedication to fundamental physics. We were all interested in many things, and for instance, I was interested in biology. I thought that to study biology really I must start with physics and mathematics, and then I never ended. I was seduced by mathematics, and so I changed my original intention to become a molecular biologist. But Mitya was very strong, had very strong opinions, and his early dedication to fundamental physics is due to a remarkable popular book which he read as a teenager at the age of 13, I guess. That was a very nice book of Daniel Danin, The Inevitability of a Strange World, which is dedicated to the intellectual history of quantum mechanics. It's written in a clever way. This book is just not a simple account of facts, but you really feel that it was a drama, and this was a very impressive drama. And so Mitya always told me that that was the first impetus which made him decide that this is the thing which he should dedicate his entire life. And so he did. He never hesitated. At that time, well, I should say that in the first years of the university, physics was taught rather poorly. The general course of physics, which was taught by Count Tolstoy, well, that was not very serious. And we now people sometimes remember about Count Tolstoy, saying that this was a real intelligent, just a true, a very interesting person. I cannot confirm it. And On the other hand, mathematicians gave very bright courses which were interested from the very beginning. And so many of us were just seduced by mathematics. Mathematicians, they have the choice, they could make the choice of best students during the distributions of students over the years. Mathematicians have got some preference. And Mitya was indignant about the story. He never liked that in physics department mathematicians have some preference over true physics. One couldn't help it because physics was taught so poorly. But he was never seduced himself. Now the story about Danin's book had an unusual continuation much later, when Mitya was working in Denmark at the famous Nardita Institute, which was just part of the institute once founded by Niels Bohr himself. At that time, he was offered a very unusual privilege. The famous beer producer Jacobsen, who founded this Carlsberg factory of beer, he donated his personal villa to the Danish Academy of Sciences with the intention to house there prominent scientists. And the first scientist who had been given that privilege was Niels Bohr himself, who lived there up to, until his death, and then his wife remained there too until her death. And after that, the villa was reshaped, and it was offered to prominent scientists from abroad to be housed there for a while. And I believe that Mitya was the only and the first and the only Russian scientist to be housed in that villa. And this story about Carlsberg villa was described in great detail in Danin's book. And so he was very much impressed by this unprecedented turn of the story, because it started with his boyish, he read this book as a boy and he was impressed, and then finally he got to that same place and was placed in the former apartment of Niels Bohr himself. So he did not stand to the temptation to write a personal letter to Danin, telling him the story that he was just at the very origin of this unusual turn of events. And Danin was very much impressed. He even published an article in some newspaper about it. And I was told that some of Mitya's colleagues here at the Nuclear Physics Institute were not quite happy with that story. They presumed that Mitya was lacking modesty while writing this letter to Danin. Well, nothing of the kind. It's a boyish story. Just he felt in love with physics as a mere boy, and to a certain extent he remained a boy up to the end. Now, I should say, well, Misha has already told much about this intellectual atmosphere of Dьяконов's apartment at the Suvorovsky Avenue. I always considered this as a kind of intellectual feast, this table talk, which was dominated by some restrained remarks by Igor Mikhailovich, which were all of the kind that you would think about for the next week. That is something that is quite unforgettable. And of course, well, as in Dickens' novel, this was the best of times, this was the worst of times. This was the best of times because we were all very young and everything was ahead of us. And also we were open to the world and to the situation of our country, of our unfortunate country. And we were, on the one hand, it was a rather painful discovery. Well, Mitya once recalls that it was in '62 when the first Gagarin flight took place, and he felt he recalled this story about saying that it was probably the only moment until 1991 that he was really proud of his country. And then the thaw ended, and many things happened, such things like the invasion of Czechoslovakia, and in a very painful way, we were discovering for ourselves a rather painful truth that something like socialism with human face is a contradiction and is something which doesn't exist at all. It's not that we were convinced of it from the very beginning, but it was a rather painful discovery for each of us. We were all very pessimistic in 1980s, especially when things grew worse, when the situation became rather bleak. It was a difficult time for the country and also for all of us. And then came, quite unexpectedly, came perestroika. And this, I should say that none of us has ever predicted it. And it was a moment of real hope. And Mitya was saying at the time that he was proud, once again, that in his country his country proved to have a critical mass of really intelligent and responsible people. That was the moment of hope in the early 1990s. And then gradually Mitya returned to much more conservative estimates, and he was saying that after all we didn't reach that critical mass, and things were starting to go in exactly the opposite direction. I was telling about this story of some kind of painful discovery of the truth which we made as youngsters in 1960s and then in 1970s and then in 1980s. We were growing older, but the situation didn't grow better. And it was one important aspect of that study of the truth was of course reading. And Mitya was in close contact with Professor Etkind, and Professor Etkind provided us with dactyl copies of early Solzhenitsyn's novels, which we were reading just from this carbon copy manuscript with handwritten corrections made by the author himself. That was a great venture. And since we were all very young, just each of us chose just a model hero, a paragon to be followed. And Mitya's choice in Solzhenitsyn's famous novel The First Circle was Sologdin. That was his favorite hero at the time. Again, it's a kind of boyish story, but it's very sympathetic. And then that was a... Now, we have some photos here. Well, I do not tell you another story, which is about the interaction and competition of two different schools of theoretical physics which existed in Leningrad. One is, of course, the famous Gribov school, which at the time was very much reluctant about field theory. And I belonged to another school, which was the school of Professor Fadeev, who was at the origin of the revival of quantum field theory in our country and worldwide. And so there was a kind of jealousy and rivalry between the elder people of both groups, because the relations between Fadeev and the Gribov seminar were always not quite easy. And Mitya was just, he didn't participate in that old rivalry. And finally, I should say that the physicists, the nuclear physicists, should accept, they had to accept that finally Fadeev was more right than they ever believed him to be. And on his side, Fadeev always told that of all the theorists from the nuclear physics department, Mitya is the one which he esteems the most and which is most close to him personally in his scientific work. So it was there were quite a few intersections and repercussions in the work of both groups. Vitya has told about their famous works about just exploring hadrons as solitons. Of course, the very idea that hadrons may appear as solitons in some more simple field theory goes back to Fadeev, who was the originator. He insisted on this idea here in Leningrad just in the early 1970s, and then it was a difficult task for him to get this idea accepted, and then finally it became a common wisdom. Although, of course, he didn't participate in the qualitative study of four-dimensional solitons and their exact relations to real physics. So it's a complicated story which I'm not quite prepared to tell you this time. I should probably show some photos here. Now let me start it. This is probably one of the last photos in this collection, which is taken during a conference here in Euler Institute in 2009, I guess. And this is Ushkova. Maybe this is the celebration of the new year of which Misha was telling. Now this is just a boat trip for children, just again much later when there were children already. And this photo is taken in 82 when we were making a short trip, three of us, Mitya, myself, and Lenya Gribov. That was in Pamir-Ala in late August 82. And 2 years later, unfortunately, they made another mountaineering excursion, and Lenya died in an accident. That was a terrible story. That again is taken during that trip of 82, together with a Kyrgyz family somewhere in the mountains. And this, again, that same mountaineering excursion. And this one is taken earlier in 1977, when we again made a mountaineering excursion, which was not quite successful because of some minor accident. Mitya injured his leg, and he was obliged to interrupt the excursion and to go back. And this photo is taken at the moment, group separated into two parts. So the three of us went down, and the other three remained in the mountains. So we are just already going back in the low mountains in the direction of Khajent. And this is the entire group. Yes, this is the group which returns. This is 76. And this photo is taken on the balcony of this Carlsberg villa. Here is the Carlsberg villa, and this is 2003. So I should probably stop here. Thank you very much.
think